when we move away from carbon and hydrogen, we get new um, considerations that we have to account for, right? And so heteroatoms, first of all, a definition. A heteroatom is any element that is not carbon or hydrogen. So like I said, organic chemists are mostly concerned with carbon, but all those other elements do show up in our structures as well. So we call those, anything that's not carbon or hydrogen, we call it a heteroatom. In general, and especially in an introductory sense, we're going to start with, right, if I draw the kind of the upper right corner of the periodic table, we've got carbon, nitrogen, oxygen, and fluorine, right? Um, we're going to treat fluorine, chlorine, bromine, and iodine. We're going to kind of treat all of these the same. So we're going to treat that as one group. But we can use what we know of valence electrons and the octet rule, etc., to figure out how many bonds we expect each of these things to make, right? So carbon has 4 valence electrons, and we know that as we move across the period, we add a valence electron every time we move to the right? So carbon has 4, nitrogen has 5, oxygen 6, and then all of the halogens, fluorine, chlorine, bromine, and iodine, have functionally 7 valence electrons, right? There are, as we get lower in the periodic table, other things start to come into play, but for our purposes, that will work just fine. So the number of valence electrons is 4, 5, 6, and 7. In order to complete their octet, bonds needed for complete octet, right? Carbon, we've already established, needs 4 bonds to complete its octet rule, right? And so we have to take those 4, it has 4 valence electrons, it needs 4 more. The way that it gets those extra 4 is through bonding, right? Nitrogen, to complete its octet, needs 3, right? It has 5 valence electrons, it needs 3 bonds in order to fulfill its octet. Oxygen needs 2, and the halogens need 1. And so once again, we have this kind of nice pattern where the number of bonds needed for a complete octet decreases by 1 as we move to the right. Okay, so what this looks like if we use nitrogen as our template, right? Nitrogen has 3 bonds, that's going to complete its octet, but it has 5 valence electrons, and so it has 3 of those electrons have been used to make these 3 bonds, but it still has 2 other electrons that were not used to make any bonds, right? The difference between 5 and 3 is 2. And what those 2 electrons are, of course, is they become a lone pair, which is the third area where um, electrons can be in organic compounds. And so the number of lone pairs in a neutral, when number of lone pairs when neutral, right? The number of lone pairs when neutral for each of these is also something that we can figure out and also follows a nice pattern, right? So the nitrogen has 2 electrons left over. We have 5 valence electrons, 3 bonds, 2 electrons left over. 2 electrons makes 1 lone pair. Oxygen has 4 electrons left over. That makes 2. So 6 minus 2 is 4. That's 2 pairs. And similarly, the halogens would have 3. And so once again, as the number of valence electrons increases, also the number of lone pairs increases when the compound is neutral. So if we have any kind of neutral halogen, like bromine, for example, that's going to have 1 bond to connect it to the rest of our structure. And then that halogen, like bromine, is going to have 3 lone pairs on it that we're going to always kind of assume are present when it's neutral. And this is great, right? This allows us to kind of, instead of having to use some kind of formula to calculate valence electrons and bonds and bond order and lone pairs and all of that stuff, we can just kind of use pattern recognition to figure this out. And very quickly you will recognize that every time I see an oxygen in an organic molecule, if it is neutral, it has these 2 bonds next to it and it has 2 lone pairs, right? There are other ways of having two bonds to oxygen, right? We can also have a double bond to that oxygen. That can have two bonds and two lone pairs that way, right? Double bonds count as two bonds, so that works just fine. We could have a double bond to a nitrogen as well. That can still work. It just needs to have three bonds total and have its one lone pair. Right? And so we can have double bonds, we can have pi bonds that exist with heteroatoms as well as with carbon. Right? So we can have sigma bonds, we can have pi bonds, we can have lone pairs, all having to do with these heteroatoms. Once we start introducing pi bonds, we need to think about overall hybridization. Right? We can use hybridization in the same way that we did with carbon. Excuse me, I'm going to finish off these structures here, right? And it's going to follow the same rules. The only difference is in hybridization of heteroatoms, we count lone pairs with sigma bonds, right? So we have these two oxygens here. We can look at these two oxygens. This oxygen has two sigma bonds, sigma bond here, and two lone pairs. So that is four total sigma plus lone pairs and zero pi bonds. Right? So four sigma bonds plus lone pairs, no pi bonds. This oxygen is sp3, right? Much like the carbons that we looked at, right? When we had an sp3 carbon, that sp3 carbon had four sigma bonds and no pi bonds. Carbon was easier because we didn't have to consider lone pairs, but we could very easily incorporate those lone pairs in there. This oxygen has three sigma bonds and lone pairs, right? It has one sigma bond connected to it, two lone pairs, so it has three total there, and it also has one pi bond. And so this oxygen we would expect to be sp2 hybridized, and in fact that is the case, right? So the carbon that is connected to is also sp2. We have sp2 carbon, we have sp2 oxygen. Similarly over here we have sp2 carbon and sp2 nitrogen. Right, so the nitrogen is sp2 because it has a pi bond, but it also has sigma bond plus lone pair. So it has three sigma bonds and lone pairs. It has one pi bond. So that nitrogen is sp2. So we can use hybridization to describe not only carbons, but also heteroatoms. The thing that heteroatoms do that carbon does not do quite as much is we have to think about formal charge. So heteroatoms and formal charge. So in our table on the previous slide, we looked at how many electrons are needed to fulfill the octet rule, how many bonds are needed to fulfill the octet rule, and also how many lone pairs are needed, right, in order for the compound to be neutral. Now we consider what happens when they're not neutral. First rule, heteroatoms always satisfy the octet rule. Right, this one also gets some stars. This is an important statement. What this means is that any heteroatom will always have kind of four pairs of electrons surrounding it, right? So the number of sigma bonds, pi bonds, and lone pairs, sigma bonds plus pi bonds plus lone pairs will always equal 4 when we talk about heteroatoms, right? It has to always have four of those things surrounding it. Right? When we talked about carbon, we said that neutral carbon will always have four bonds to it, which means it always has sigma bonds and pi bonds equal to 4. But heteroatoms, whether they are charged, right, if they have a positive charge or a negative charge, or if they're neutral, the number of sigma bonds plus pi bonds plus lone pair will always equal 4. But we can move things from one category to the other, right? So we said a neutral nitrogen has 3 bonds and 1 lone pair. So this is an sp3 nitrogen, right? 3 bonds, 1 lone pair. This is neutral. But if we say, well, instead of having 3 bonds, 1 lone pair, what happens if nitrogen has 4 bonds? Right? Now, this still satisfies the octet rule. We have 4 sigma bonds surrounding this nitrogen. This nitrogen is still sp3 hybridized, but the formal charge, it no longer has the right number of electrons to satisfy its valence, right? So we've converted that lone pair into a sigma bond. This nitrogen is now positively charged, right? So it has a +1 on nitrogen. Inorganic, we're only ever going to be dealing with +1s or -1s. You're never going to see a +2 or -2. That's for the metals, and we're just not going to talk about metals very much in this class. We can also make an sp3 nitrogen that's negatively charged, and you can probably predict what that would look like, right? If we take 2 sigma bonds to the nitrogen and add 2 lone pairs, 2 sigma bonds, no pi bonds, 2 lone pairs, we're still satisfying the octet rule, but now we have more electrons than valence would suggest, and so with an extra electron, that means we have a negative charge on nitrogen. So when we have more lone pairs than we would normally, than we had calculated on our table over here, right? So when we look at our table for nitrogen, we predict 1 lone pair when neutral. If we have 1 lone pair, it's neutral. If we have 2, it's negative. If we have 0, it's positive, right? So 2 is negative, 1 is neutral, 0 is positive. This is true regardless of hybridization. So we can also do an sp2 nitrogen, and we can do the same thing. Right, so a negatively charged sp2 nitrogen would have a pi bond, a sigma bond, and 2 lone pairs. So 1 sigma plus 1 pi plus 2 lone pairs. That still equals 4, still has the octet rule, but because it has 2 lone pairs, that tells us that it's negative. Right? A neutral sp2 nitrogen has a pi bond, 2 sigma bonds, and 1 lone pair. But is neutral because overall it satisfies the octet rule. It has 1 lone pair. It's neutral. And then, of course, positive charge means it has no lone pairs. And so an sp2 nitrogen now has 1 pi bond plus 3 sigma bonds plus 0 lone pairs. Right? So the 0 lone pairs is what clues us in that this is a positively charged nitrogen. The 1 pi bond tells us it's sp2. Right? The 0 lone pairs is what tells us it's positive. And that's what gets us there. Okay, so that's formal charge. We can do this with oxygen. I will leave that to you to do this with oxygen and the halogens as well. You would see a similar thing, only the neutral would have a different number of lone pairs based on the table on the previous slide.